Now, welcome to electrical machine lecture. Today, we are going to discuss the power stages in DC motor. The power stage in DC generator already discussed the same because the construction of DC generator and DC motor is same, or simply the DC machine. It may work as a motor or generator. As the physical parameter, physical part of the machine is same, therefore the power stages and losses almost same. Only the difference is that in case of motor, the input is electrical power and the output is a mechanical power. Therefore, the power stages is just reverse. Now, see in the power stage in this figure. In this figure, the power stages, the input to the machine is the motor input in the form of electrical energy, which is V into I. Power input is equal to V into I is the watt. So this much watt is the input to the motor. Whereas there is some copper losses which is going to occur in the armature as well as the field winding. In addition to the copper losses, there are iron losses also there. So the copper losses, if you subtract the copper losses, that is the gross mechanical power developed by motor. So it is the mechanical power developed by the armature. So this is the gross mechanical power developed is nothing but the back EMF into the armature current. No doubt the back EMF magnitude is smaller than the supply voltage, and armature current, the motor take the current from the mains is the armature current. Now, if you subtract the iron and frictional losses from the gross mechanical power developed, we get net mechanical power developed by the motor in the form of horsepower or watt. So horsepower multiplied by 746 watt is nothing but the mechanical power output for the motor, or it is a torque, shaft power torque. Now see in this diagram, DC motor, suppose this is the motor and DC generator is same, DC motor. So the motor and generator is same. Simply there are losses which is going to occur in the armature structure. Therefore, it is called as the iron losses. Copper losses in the field winding. For the DC shunt motor, it is constant, whereas for the DC series motor, it is a variable one. Now, copper losses in the field winding, copper losses in the armature winding. The copper losses in the armature winding is more as compared to the shunt field winding. So this is the total copper losses. Iron loss, which is going to take place in the iron material. It is a laminated one to reduce the eddy current and hysteresis loss. But when the rotor rotates, there are some frictional and windage loss which is going to occur. That is wear and tear is going to occur over the brushes, and therefore this is called as a iron and frictional losses. This iron and frictional losses also called as a stray losses. Whereas the copper losses, many times it is depend upon the load condition, therefore it is a variable one. Whereas as long as the voltage and the speed of the motor is constant, the iron and frictional losses are constant. So this is the one power stage. It can be explained some more elaboration. That is the DC electrical power, which is nothing but the V into I, power input to the motor. Now there is a field copper loss. Field copper loss, we write the equation, it is I square RSH square RSH, sorry, ISH square RSH. Then armature power input means the power is going to transfer from the field winding to the armature. That is a rotor, and in the rotor there is an armature winding. So armature copper loss, so it is a IA square RA, armature copper loss. Now after subtracting the armature copper loss, we get the gross mechanical power developed. So this is the gross mechanical power developed, which is EB into IA is the gross mechanical power developed. After gross mechanical power developed, there is a frictional and windage losses. Frictional and windage losses, And after frictional and windage losses, we get the mechanical output in the form of BHP, British horsepower, or HP. And if you multiply the 746 watt, then it is comes into the power. It is the output power. Say this is P out, output power, and we get shaft power outputs TSH. Similarly, the torque developed by the armature we can represent as a armature torque. So the difference of these two, armature torque and the gross mechanical power developed. Just we write here, say gross mechanical power. So power loss or torque loss is equal to TA minus TSH. So this is the torque loss in the machine. So this is the, say, some different stages in the DC motor. Now, what are the losses? Same, because the construction is same. Part of the DC machine also same. DC machine and DC motor, that is DC motor and DC generator is same. Therefore, the losses in the DC motor is same. Only the difference is that the losses in the DC motor is reverse, because in case of generator, it is going to deliver the current from the armature, whereas it will consume the current from the supply. So the losses in the DC machine or DC generator and the DC motor is same. First is the electrical losses, that is the copper loss. This copper losses comprises of square of the current, armature current. So it is IA square RA, whereas the shunt field copper loss ISH square RSH, or it may be a VSH into ISH. Now series field copper loss, it is ISE, series field current multiplied by the series field resistance. This series field current may be equal to the armature current if it is a short shunt. If it is a long, if it is a short long shunt, and if it is short shunt, IA and IC, there is a slight difference. Now magnetic losses, iron and core losses, which is equal to the AD current loss and hysteresis loss in the armature. Mechanical losses is the rotational loss, that is the frictional and windage loss. So this is the some losses. The numerical based on these losses and power stages we will do later on. Now we will consider the torque, the topic torque. Therefore, some small idea is needed to understand the torque. So this is the some basic idea or power stages in the DC motor. So now torque. Now, what is torque? Torque is it is nothing but the turning or twisting moment of force about its axis, because the rotor is a circular motion. It is not a linear motion, it is a circular motion. So we will say the torque means the turning or twisting moment of force about an axis. That is the axis of motor or pulley. It measures by the product of force and radius at which the force acts. So as per definition, let R is the radius of pulley, radius of pulley, and F is the, it is in meter, is a force in Newton, and the rotor runs N, or okay, N is the speed of rotor, in RPM, revolution per minute. Please wait. This one note is not responding. It takes few minutes. Okay, RPM, revolution per minute. Now, as per the definition, torque is equal to torque equals to force into radius. As we have written, it is the product of force and radius at which the force acts. So it is in Newton meter. It is in Newton meter, which is equal to force F into the radius. It is in Newton meter. So this is the torque. Now, therefore, work done. Therefore, work done by the force in one revolution it is equal to force into distance it means that it is the condition so this is the pulley whose radius is r and force is acting. This is the force it is acting and let it is running at a speed which is equal to n in rpm. So this is the speed. So this is the pulley. Some pulley, it is connected with the motor. So now we can write as when r is the radius, so it is equal to f into twice pi r. This is the circumference as it is energy, so it is in joule. So this is the work done. Now, therefore, power developed is equal to force multiplied by twice pi r into n. Now it is comes in joule per second, and it is written as a, or it is the power. It is a power. It can be written as a watt. So which is equal to F into R, force into radius multiplied by twice pi n. Twice pi n. So this much is the watt. This is the power. So now the twice pi n, where twice pi n is the angular velocity, which is denoted as omega in radian per second. Radian per second. So twice pi n is the radian per second. Therefore, power developed it is written force into radius is nothing but the torque. So it is torque multiplied by omega. It is in watt. So power developed is equal to torque into omega, or so we'll have a one equation. This is very important equation. Say we write power P out, power output, or say P over this one. Now we will give the name later on. So this is one important equation. Power is equal to torque into angular velocity. P is equal to T omega. Now, omega, now n is the speed in RPM. Then we can write omega is equal to twice pi n upon 60. It is in radian per second. We can write this one. So now the power P is equal to, what is the value? T into omega. So T, or we can write as a omega T, which is equal to omega is twice pi n upon 60 into T, which is equal to P. So this is one more equation or relation. We will elaborate. This is now in this case, we can write as torque is equal to what is the value of T? It is 60 upon twice pi into P upon N, where N is the RPM. And therefore, torque is equal to 9.55. If you put the value of twice pi and 60, it is equal to P upon N, where N is the speed in RPM and N P is the power output. Now we can write torque is equal to 9.55 into power output divided by speed in RPM. So this is in the Newton meter. So this is a very important relation. It is going to use in many application, many numericals. This is the one. Now, because of this one, now we try to develop the armature torque. Armature torque of motor. Now, using the above equation, same relation, we try to find out the relation of armature torque. Let TA is the armature torque developed by armature torque developed by armature. No doubt it is in Newton meter. It is in Newton meter. And speed of rotor in RPM, then we can say that power developed by armature, power developed by armature equals to TA into twice pi n upon 60. That is the simple from the same relation, torque power is equal to omega t. We know that power developed by armature equals to back EMF into armature current. See, in this block diagram, what is the power developed by armature? Power developed by armature is nothing but the back EMF into the armature current. After subtracting the friction, field copper loss and armature copper losses, iron losses, we can say that the gross mechanical power developed or the total power developed by the armature is back EMF into armature current. This is in watt. Now this is power developed by armature, TA into twice pi upon 60 and EB is equal to same value. So now say this equation number 1 and this is equation number 2. equation number 2. So equating equation number 1 and 2, equating equation 1 and 2, we can write as TA into twice pi n upon 60 equals to EB into IA. Now we know that the back EMF value, which is equal to the TA into twice pi n upon 60, back EMF is nothing but phi Z n P upon 60 into A armature current IA. So by equating these two values, armature say 60 get cancelled. Now speed get cancelled. The speed will not be there. And all these things. So we get armature torque TA equals to the numerical value 0.159 by calculating the pi value and all these things. Phi ZA ZIA into P upon A, this much Newton meter. Now look at the equation of armature torque. Say we will now let this is the equation. Look at this equation. We found that Z is the total number of conductor. Once we construct the motor, the total number of conductor will remain same. Once we design the motor, number of pole and number of armature parallel path will remain same. So this parameter Z, P and A are some constant for particular motor once it is designed. Therefore, the armature torque TA, or okay, we will write this sentence. For motor constructed Z total number of conductors on armature, P number of pole, and A number of parallel path will remain constant. Therefore, armature torque TA is directly proportional to flux into armature. So this is our required equation. So armature torque armature torque is directly proportional to product of field flux or flux per pole. Either it may be a shunt motor, either it may be a DC series motor, any type of motor. Torque is directly proportional to armature current and field flux. So this is the relation. Now from this one, we can say that armature torque TA is equal to, from the basic equation, we can write as power into power divided by omega, or it is 9.55 into power gross armature power divided by speed in RPM. So we can write the above equation as armature torque TA equals to 9.55 into EB into IA divided by N. It is in speed. So this is the armature torque. So we can calculate the armature torque from this relation. Or we can write as shaft torque, means the torque available at the shaft of the motor, that is the useful torque. So shaft torque, or it may be called as a useful torque, equal to, that is it is represented at TSH equals to 9.55 into, instead of the gross armature power, that is the power output, total power output, P output of the motor, divided by N. N is the speed. So in this way, we can calculate the power output from the all this one. Either it may be the total gross or gross mechanical power developed, TIA, and the shaft power output. And the difference of these two shaft is the torque loss due to iron and frictional losses. So we can say that the loss TA minus TSH is the torque loss. It is a loss of torque loss due to mechanical losses. It is in very simple. So from this is the, say, by which we can go for the different type of numerical based on this one. So we can calculate one example. A 250 volt 4 pole 4-pole wave wound DC series motor has 782 conductors. 782 conductors on its armature. On its armature. That is Z is equal to this one. It has armature and series field winding. Armature and series field winding resistance. Winding resistance of 0.75 ohms. Means the total resistance of armature and series field is this one. The motor take current of 70 ampere. Sorry, it is a 40 ampere. It's 40 ampere. Estimate. Please wait. Estimate the speed and gross torque developed if it has the flux per pole is 25 milliweber. Is the 40 ampere. 40 ampere. Estimate its speed and gross torque developed if flux per pole is 25 milliwave. So what is given? Here it is given that voltage is equal to 250, P is equal to 4, number of pole, wave wound. Wave wound means A is equal to 2, A is equal to 2, and armature and it has a conductor. Total number of conductor is 782, and armature and field resistance Ra plus Rse, it is 0.75 ohms. Whereas the armature current, here armature current and series field current is same, which is equal to 40 ampere, and flux per pole phi is equal to 25 milliweber, which is equal to 25 into 10 raised to minus 2, sorry, minus 3 Weber. So this one. We know that back EMF EB, which is equal to phi Zn P upon 60A. P upon 60A. And if you put the values for this one, we able to calculate the back EMF. So as we don't know the value of speed, so it is not possible to calculate the back EMF. We can calculate the back EMF as it is a series motor. It's a series motor. It having armature resistance, series field resistance, and it is excited from the DC supply, whose values is 250 volt, and it takes the current of 40 ampere. So now it is equal to back EMF EB. It is opposite to the supply voltage. This is the voltage V, and it is opposite, it is the back EMF. So EB is equal to, we can write V minus IA RA plus RSE. It is the series resistance because it is a series motor. So it is 250. It is a 250 minus armature currents 40 into 0.75, and it is comes 220 volt. So now this is 220 volt, and we know that the armature torque TA, just we have derived the equation. It is 0.159 into phi into Z into IA and P upon A. So if you put the value, we got the speed. What is the, that is the torque, this one. So we can write as phi Zn P upon 60A. We got the value. And from this one, if you put the value of back EMF over here and calculate the value of speed, so you can calculate speed is equal to speed. We can calculate the speed in the form of same equation, and if you put over this one, we get the torque is equal to 249 Newton meter. So in this way, there are numericals. There are some numericals are there, and next time we will see some more numerical based on the torque and the for the DC series and shunt motor. The basic equation of torque will remain same. That is T is equal to armature torque is equal to, or it is proportional to armature current into shunt field flux. So thank you for today's lecture. We will continue with the same topic and some numericals.